here's problem 3 of homework number 4. And I don't know if I've done this problem this way before. I kind of made a little change to it. So we know the initial velocity of Tiger Woods' golf ball, and we know the angle it is off the club face right here. And I pulled this off of some internet site. I think this was actually back in 2008. Just some website referred to the thing. Anyway, we want to find the distance the ball will travel in the air over flat ground, right? So there's nothing, no elevation changes. He's not hitting upward. We just want to find that distance. And we want to find the radius of curvature of the ball's path at the highest point of its trajectory. We're going to find that's actually not that difficult to do. And then we want the radius of curvature of the ball's path just before it lands. And that's going to require a coordinate transformation array, or at least I require you to do it. Okay, so let's take a look here. And I've written the problem out. And some preliminaries I could have gotten out of the way. 183 miles per hour, 183, let's do in feet per second. So that helps. So it's 5,280 feet per mile, and then 3,600 seconds per hour. So we end up getting 268.4 feet per second. Okay, so in order to do that is a projectile motion problem. You would think it'd actually be a pretty simple one, but what you basically have to do is find the amount of time it's going to be in the air, and then you can find in the y direction, and then in the x direction you can plug that time in, and you can figure out what the distance is going to be. So in the y direction, the initial and the final is going to be equal to 0. That actually makes this a little bit easier to do, this particular problem. When there's elevation change, it makes it, I think it turns into a quadratic equation. I think I have this correct. By the way, it might behoove us, which is a great word, to have the x and the y velocities from this, right? So to turn this, that's probably a good idea to start out with. So we're just going to take our 268.4 and take it times, this is the x direction, so the cosine of 8 degrees. And then 268.4 times the sine of 8 degrees, right there. So 8 cosine times, that's 200, whoop, I started to write the 6 first. Momentary dyslexia. 265.8 feet per second, and sine times that's only 37.35 feet per second. Okay, so when we do this, let me write out the basic equation. The Vy times time minus 1/2 g times t squared, right? But it starts, the y starts at 0 and it ends at 0 when it's flat. So we take our 37.35 times our time. It's going to be minus 1/2, and gravity in US units is 32.2 feet per second squared, t squared. You can see what's going to happen here is that one of the t's is going to be we're able to cancel out one of the t's. That's pretty nice. So I could just solve directly right here, right? I will. Right, so we could just say one of those goes away. Nice. So we're just going to take 2 times 37.35 divided by 32.2. So it's going to be close to 2 seconds, right? So we're going to multiply that by 2 and divide by 32.2. Divide. So it's going to be in the air for 2.320 seconds. Note that if there was an elevation change, these wouldn't be 0, so this time wouldn't cancel out. So what you need to do is find the roots to be able to find the time, right? And one of the times is often negative, so it doesn't make any sense. So we just throw it away. But this made it easier right here. And so now we want to get the distance that it traveled right there. So the distance that is traveled is just going to be found from v in the x direction is going to be equal to initial velocity. Nope, sorry, duh. Never mind. The velocity in the x direction is the same, right, all the way through. So we want to get the x is going to be x naught, which we'll treat as 0. I'm just going to start at 0. Does that make sense? Plus the velocity in the x direction initially times time. So that's pretty easy, right? Just 265.8 times 2.32 seconds. So I have that. I still have those in my stack. It's kind of nice. I just hit multiply, and we're going to say that it's 616.7 feet. Just out of curiosity, divide that by 3, and that's only 205.6 yards. That's interesting. I think there might be a mistake here somewhere, because I know he hits it. This should be come up to 300 yards. Let me pause this and see if I made a mistake somewhere. I'm almost positive there is. But, you know, mistakes will happen. I'll use here. I guess what's happening is I should mention that the spin rate in golf, the spin of a golf ball can generate lift, right? So this is correct. It is like 206 yards of carry, but with a spin rate that could also generate some lift, so it actually is up in the air longer. But we're just treating the thing as if it's just something moving through the air. All right, I think I have that correct. So anyway, this is the answer to part A right here. So part B, interestingly enough, is just going to be, if we were going to look for the curvature of something, right, we need to find what the acceleration is going to be at the top. Well, that's just going to be the acceleration of gravity. So if we know the horizontal velocity remains the same everywhere, right? It just, as long as there's no air resistance, which of course this is an idealized case right here. If the acceleration in the normal direction is going to have the velocity squared divided by the radius of curvature, right? So we could find the radius of curvature if we take the velocity and divide it by the acceleration, right? Just swap them out there. Well, in this case, it's going to be 265.8 squared divided by and 32.2. So let's say 265.8 and square it and divide it by 32.2. Sure enough. So this is very large radius of curvature because the arc is very kind of flat. So we get 2,194 feet. Okay, so we also want the radius of curvature now for the when it lands. Now, this is kind of like we could make this a lot more complicated than it need to be. But if the launch angle is 8 degrees, then the returning angle is going to be 8 degrees. Now that's an idealized situation. It actually drops down more because of the combination of lift that's generated, right? and also a slight deceleration in the x direction because of actual wind resistance that takes place. So, but anyway, we're going to say as it lands right there, let's see, I already have the sketch out there here. So like if this is 8 degrees right there, this is 8 degrees. So what we want to do here is find, here is the direction of the tangential right here, and here is the direction of the normal. And maybe I should have drawn that in the other one too, right? Here's the tangential, here's the normal, here's the tangential, ET, and the normal was in that direction, right? EN. So in this case, right here, and I've exaggerated the angle a little bit, that's much bigger than 8 degrees right in here. So we know that right here has to be 8 degrees. So we do our coordinate transformation array, and we know that acceleration is still downwards, right? So that's, so we would say that the acceleration, regardless of where you have it right there, is going to be negative 32.2 J, right? The acceleration of gravity, only acceleration there. So let's do the coordinate transformation array as part of this right here. So we get the, let's do the, here's the I and J, and now make it exaggerated here. Here's our T, ET, and something like that for our N. Oops. Something like that, all right. EN. Here we're going to go in there, and I can extend these up too. Wow. And so the angle is this one right there. I'll call that the theta. Right, so this also makes this one theta. I didn't draw that perfectly. They should be the same angle right in there. So the coordinate transformation array, getting practice with this is a good thing. Should have made that bigger. Oh well. Look it down here. Already feels like it's been a long day. I spent a lot of time with an advisee this morning. Complicated. There you go. So let's once again make an I and a J here, and make ET and EN. And so the oh, look at that. Look how messed up I am. I need some more coffee. There you go, I and J. Oof. So the ET in the I direction is just going to be the cosine of that angle. And the ET is going to be the negative sine of theta, right? Because it's going down in the negative J direction. The EN is also negative, and because it's going in the I direction there, it's in a negative I direction. It's going to be opposite from this angle. So it's the sine, and it's also negative, and it's the cosine. Right, because EN. The only one we really want is to get it in the EN. That's what we want to try to find, right? So we know that this one is acceleration right here, so we want to convert this into ET and EN, so I'll go ahead and do that. So the acceleration, which we know is G, I could have written it as G, but I made it a vector acceleration there. In the I direction is going to be negative 32.2 times the negative sine of theta. So negative 32.2 times the negative sine of 8 degrees, and did I just mess that up? No, that's the tangential. Okay. All right. And then we're going to have, and there's nothing in the I direction there, so we don't have to worry about that column at all. But here's the column, so we're going to plus, we'll take our negative 32.2 again, and put them against our negative cosine of 8 degrees. And this is actually the only one we want, but that's all right. So now we've converted gravity into this coordinate system. So we have sine of 8 times 32.2, boom, something very small, it's a positive number, 4.481 ET, and then plus 32.2 and cosine times, all right, so we find out that it's 31.89, so it doesn't really even change much. So here's in the n direction, so we know that that right here is AN, so we could do the same thing we did up here. We can find that rho is going to be equal to v squared over AN. Here's a thing that we need though. Oh yeah, we need the velocity. We need what the final velocity is in the y direction. So how do I do that? Oh, that's actually it's kind of interesting here. It's kind of simplified. The velocity in the it's kind of sad because there's no change in the x direction, and in the y direction it's going to have the same velocity upwards here. It's going to have the same velocity down over there. So actually the magnitude of this is actually the total velocity. It'll still have the same original velocity magnitude coming into there. So that's 268.4 squared, and divide it by 31.89, and let's see what the values are. 268.4 squared and 31.89 divided, and we get 2,259 feet. So our answers A, we have, I'm just going to write it as delta x is equal to 617 feet. B is going to be 2190 feet, and C is going to be rho is equal to 2,260 feet. I don't know if these are very exciting values. I like to try to come up with something, problems that might have some kind of interesting or some kind of interest in them, and so I like Tiger Woods. I hope he heals and maybe can play golf again with his damaged leg, but we'll see. Anyway, there you go. Also, I had some some stats right here off of golf. Let's see, this is TrackMan, and this is like your average pro, and you can see that they have this 113 club speed, and so the ball speed's 167, so we're talking about 183, and the launch angle is like 10.9 right here. But see, the spin rate, that helps with generate lift, right? The ball is spinning, and that kind of helps to cause some amount of lift that takes place. You can even see that by way of its land angle is 38 degrees versus a launch angle of 10.9. And we know that they would be equal to each other if it was just purely a trajectory thing. So let us be done with this video.